Okay, so we're going to start out with a physics lecture here. This is going to be on X-ray production and generation. So just starting out with some real background stuff that's really irrelevant to how we practice, but potentially testable. What is electromagnetic radiation? So electromagnetic radiation is basically a wave of energy. Okay, and unlike sound, it does not require a media to travel in. It can travel in a vacuum. And the velocity is fixed, which is the speed of light, 3 times 10 to the 8th. So, reviewing some vocabulary here, the rate of change, sort of up and down through one cycle here, is described as the frequency. And the length between one peak and the other peak is described as the wavelength. And then there's this formula which describes the velocity, which remember is fixed, where frequency times wavelength equals velocity. So because it's fixed, as one goes up, the other must go down. And that's a relationship that's sort of useful for describing the properties. So, as the frequency of the wave increases, the wave becomes more energetic and will have the ability to potentially remove electrons from an atom. And this is called ionizing radiation. So when people say there's ionizing radiation, that means that there's enough energy there to rip an electron out of an atom. And there's a certain quantity of energy that is required to do that, which is 15 electron volts. So you need a photon with at least 15 electron volts to become ionizing. So just looking at this real fast, X-rays are ionizing. But a radio wave is not, but they're all on a spectrum of electromagnetic radiation in that direction. So here we go. We've got sort of a Bohr model of an atom, where a nucleus in the center with protons and neutrons and electrons on the outside. And if we had a photon of energy that comes in here, and it's strong enough, like we said, to knock one of those electrons off, that would be considered ionizing. So 15 electron volts, said that a couple of times now, is what you need for ionizing radiation. So let's take another look here. So you may remember that there are different orbits for electrons, and they've got randomly assigned alphabetical letters to them. And the general idea is that, remember, electrons are negatively charged, right? And the nucleus is positively charged. So they want to be as close to the nucleus as possible, opposites attract. So the ideal situation, or ideal shell to live in, is the K shell, the closest one to the nucleus. That's the one that they all want to be in. And that one is the hardest to remove. And because of that, in other words, think about it like this. You've got a really nice apartment, and you really, really like your apartment. It's really close to work, and it's super nice, and the neighbor, the female neighbor is incredibly hot, or male neighbor is incredibly hot, and you like looking at that person, and whatever. Lots of reasons that you like living in this apartment. You don't want to leave. So to get you to leave, somebody would have to pay you a lot of money, right? You're not going to just leave. Somebody's going to have to come up with a bunch of money to make you leave. You're not leaving on your own terms, basically, or someone else's terms. But if you had a shitty apartment, one that you didn't really like living in anyway, and somebody was going to pay you to leave that, you'd be like, sure, $10, I'll leave. I don't like staying here anyway. So the nice apartment is this one. That's the one that, that they all want to be in. And the shitty apartment is this one. In other words, it requires less energy to knock off an electron in an upper or higher shell or higher orbit than it does to knock off one of the lower ones. And if one of the lower ones happens to leave, then one of the upper shells is going to jump on that to be able to get down there. And when it does that, there's a change in energy level. And that energy has to go somewhere. Remember that there's this rule that says you can't create or destroy energy kind of thing. It just has to change form. So it can't just disappear into free air. Something has to happen. So if there's a significant change in energy, you can produce a characteristic X-ray. So something like this. That one's going to drop down there. There you go. And then that free energy comes off in the form of an X-ray. Now, why did it drop down? Because, let's pretend that somebody, there's an apartment that you really want to live in. Somebody else is living there. As soon as that person moves out, you're going to move right in, right? So, and because there's a change in energy, like I said, that has to go somewhere. Where does it go? It becomes an X-ray. So that is how a characteristic X-ray is formed. And we'll talk about that a little bit more later. But I am going to say just one more thing about it, which I'll mention again later, but repetition is key when learning anything, especially physics. That energy difference and that characteristic X-ray is characteristic for the atom that you're in. In other words, an X-ray made from tungsten is going to be different than an X-ray made from radium or something else. So that's why that word characteristic, it means it's characteristic, and so the target that is generating the X-ray will create a characteristic spectrum. To be continued. All right, so how are X-rays actually generated? Well, they're made by this process called thermionic emission of electrons. Basically, what happens is you take a filament that's made of tungsten. Why is it made of tungsten? There's a couple of reasons it's made of tungsten. But one of the main ones is that it can tolerate heat. It has a very high melting temperature because it is going to get really, really hot when it gets hooked up to this energy source. Now, sometimes they'll put rhenium in there also, and the reason that they do that is to keep it from cracking when it heats and cools and heats and cools, because it can tolerate the heat, but sometimes that temperature change causes it to crack. So they'll mix a little bit in there, sometimes like 10%. You'll read that some places. So a current is applied, something like this, and it is applied across the filament and heats it up. And even though it's considered a small current, it still gets really hot. How hot are we talking about? Like 2,000 degrees, like super duper hot. So because of that, you're putting a lot of energy in the system, and you're making the electrons in tungsten very energetic until they actually boil off. So that's this idea of thermionic emission of electrons. So there, we're boiling some electrons off. There they go. Off to do some work. Okay, so here's a look at the whole device. Now, the filament there we already showed is the yellow thing, and that's attached to some kind of an energy source somewhere. And these red things are cathodes. In this situation, they are negatively charged. Why would you make them negatively charged? Because you want them to push the negatively charged electron towards the anode, which is positively charged. Now this whole system is in a vacuum, by the way. Why would you put it in a vacuum? Because you want to reduce friction and that kind of stuff. So you want those electrons to be able to fly across there really fast. Now the anode is also made of tungsten. Just like the same thing that the filament is made out of. And it's made out of tungsten because it has a very high Z, and that has to do with X-ray generation, which we'll talk about a little bit later. So we've got this system here, and we've got electron. It gets pushed from the cathode to an anode, strikes the anode, and that generates one of these characteristic X-rays, among some other types of X-rays as well. So And what's actually happening behind the scenes there is, you've got this high-powered thing. It's coming in. It's knocking off one of those inner electrons. You've got one that drops down, takes the good apartment. It's got to give off some energy. How does it give it off? Gives it off into an X-ray. So as the electrons actually hit the target, they have all this kinetic energy, right, as they're traveling, and because energy can't be destroyed, it's got to be transferred, and it's transferred in 3 basic ways. So here we go, flying across here, 3 basic ways. So excitation, ionization, and radiative loss, which is sometimes called Bremsstrahlung losses, which is a fancy word that means breaking. And we're going to talk about how X-rays are made in some of these and some of them are not. So the first one on the hit list is excitation. So another Bohr model of the atom here. Let's take a closer look here. And now we are going to see a situation where you've got energy coming in, striking an electron. It doesn't have enough energy to actually escape completely. Like, you paid him some money, enough to temporarily leave his house, but not enough to leave the state. So he just bumped up into sort of a medium level apartment, and then as he gets his senses, he shifts back down. And this isn't enough energy to... So there was an energy loss there. Remember, he had energy transferred. It has to go somewhere. As he drops back down, he's got to get rid of some of the energy, but it's not enough to create. It's not enough to create an electron or an X-ray. So it comes off as like a photon or as heat. So something like that. So sort of no X-ray produced is the bottom line. So going through that again, electron comes in. It's not energetic enough to make it leave. It moves in sort of an intermediate level apartment. It still has that energy. It was made energetic by that strike. But then as he gets his senses back, he realizes that he really liked this house. So he drops back down to that, has to get rid of that energy somewhere, but it's not enough to make an X-ray. Instead, it comes out as heat or a photon. No X-ray is produced with excitation. All right, so here's our next category, and this is ionization. And as I mentioned at the very beginning of this lecture, ionization means that you do have enough energy to eject an electron. So he had this 15 electron volts. He's able to leave. Now he's left, so what's going to happen? There's a vacancy in that apartment. He is going to come down here and take it. Now he's given up some energy. Well, where does that going to go? It's going to leave in the form of a characteristic X-ray. So we do have an X-ray produced this time. So ionization does produce an X-ray. Excitation did not produce an X-ray. So reviewing some of the stuff that we talked about earlier again, when we lose an electron from one, the next electron comes down, get a characteristic X-ray. This is characteristic for the material that you're using. So, for example, the K-shell binding energy for tungsten is 69.5 keV. That is what is required to generate an X-ray using tungsten. 69.5 keV. You can't have a... so the energy coming in has to add up totally to the energy going out. You can never have more energy coming out than you put into the system. So in other words, no created photon can have more energy than the incident electron, which in other words, it can't be more energetic than an electron was coming out. And why does that matter? Because the whole system can be you can control how much energy those electrons have by turning up the juice. So you can turn up the kVp, you'll hear that term used, on the X-ray generating machine, and that makes the X-rays go, or the electrons go faster and faster and faster as they come through. So you can have a difference there. So that's something that can be modified by the system. But the X-ray that comes out can never have more energy than the electron that came in. It makes sense when you think about it. But it's important to at least say it once. That way you've heard it. So 69.5, and that's specific for tungsten. That's going to be different depending on the material that you're using. What you end up getting, and we'll see this, we'll look at these things later on, especially when we're doing mammo, that there is a characteristic spectrum that is created. The peaks are your characteristic X-rays that were emitted, and then the bottom part, the hump part here, is this Bremsstrahlung continuum, and we will talk about how that's made. Now, a couple of other things. I mentioned that tungsten is used for specific reasons. One of them is that the K-shell binding energy is proportional to the Z squared. So a lower Z material gives lower energy electron or X-rays, and then a higher Z material will give higher energy X-rays. So that's another reason why whoever decided to use tungsten decided to use it. Okay. There's another thing called an auger electron. This is a thing that you'll hear about sometimes. And this is a situation where you've got your electron that comes in. It is ionizing. You do get an electron that gets knocked off, and because of that, one will drop in to take its place. But instead of generating an X-ray, it takes its energy and it transfers it to another electron. Because it's an outer rim electron, you don't have to pay those guys much to leave, right? So in this situation, you actually ionized two electrons. One came in and got knocked away, and then the energy that was transferred from one going down gave that energy to another electron, and it left. So that's bad, right? So you've doubly ionized. So this is something you don't want. You didn't produce any X-rays, and you ionize two electrons, which are going to go and damage some DNA or whatever and cause a problem. So this is bad. You don't want that. So this is another reason why you would want to choose something with a higher atomic number, such as tungsten, because elements that have lower atomic numbers tend to make these auger electrons, and atoms that have higher atomic numbers tend to make photons. So if we look at the periodic table here, you can see that it's one of the heavier elements. All right, so the last thing is these radiative losses, or Bremsstrahlung losses, and this is actually the majority of what the X-rays that are made is. Like 80% of your X-rays that are made are actually made like this. So that German word that I'm probably pronouncing wrong, that means breaking or slowing down. So as electron flies in, it doesn't actually touch anything, and as it goes around the nucleus, it slows way down, and of course energy is being taken away from it. Where does that energy go? It has to go somewhere, so it's made into a X-ray. So you can see slowing down, and an X-ray is produced. So there's three basic scenarios that can occur here. One is that the incoming electron can strike the nucleus, and this would give off maximum energy to the X-ray. The second one would be that it comes very close to the nucleus, and it gives a sort of a medium amount of energy to the X-ray. And then the third one is that it travels some distance from the nucleus and it gives off just a little bit to the X-ray. So that's why you have that continuum where it's not like the characteristics one are like the spikes, but the continuum you'll see is like that fat hump that has a broad. They're coming off at different energies because it's doing different things. Remember that electron has X. Let's say it has $100. It's got $100 worth of energy that it can give. So it can give it all to one person. It can give $75 to one person to create a $75 X-ray, or it can create a $25 X-ray and then move on with its other $75 in its pocket to catch a cab or whatever. So along that line, you develop a continuum. So to give you a practical application for this, the higher the Z, the more of this type of radiation that we're going to have. So in nuclear medicine, there's several beta emitters. Yttrium-90 would be a classic example, and because you can't just have the techs holding onto the syringe of this stuff like with their hand, they put these shields on. You may say, well, I want the thickest shield possible. Well, I want a lead shield. Well, lead has a very high Z, and that's going to generate a bunch of this breaking type of radiation. That's actually going to make things worse. So, because it's going to actually become an X-ray generator, essentially. Remember, this is like 80% of the X-ray formation. So, instead what they do is put a plastic sheet over it, because plastic has a very low Z that decreases this amount of radiation. So, the type of shielding that you want to use when you are blocking beta emitters is a low Z thing. That's why they use a plastic shield instead. That's a practical point. It's also testable. So again, this is showing you this continuum where you've got energies coming off that are the high ones, like when it's given all $100 to somebody, and then low, or it's given the $10 or $25 to somebody, and then across that spectrum. Things that are testable is that the maximum energy of that electron is the maximum KVP, and that's the peak of the spectrum. So if I would number this graph with numbers and I would say what was the maximum KVP, it would be the furthest end there. And the reason that there's a hump, they always show this sort of with a hump towards the back, is because those low energy X-rays are immediately attenuated. So that's why it creates that form like that. Okay, so back here again, we've got electron coming through, generating, it's striking, it's going through one of those three processes, two of which generate X-rays, and we've got three main factors that are determining this. They're KVP, MA, and then the duration, which is sometimes referred to as the time. So let's compare and contrast what those things mean. The MA is the current through the cathode. In other words, it's how much juice you're putting through there. It's the quantity, okay? Quantity. Now, KVP is how much voltage that you're putting between the cathode and the anode. Another way to think about this is that it's defining the maximum energy. Remember, I mentioned that several times. That was one of those things that you can modify, is what the maximum energy that you're going to distribute is. And it's sometimes referred to as the quality of the X-ray. So MA is your quantity. MAS, sometimes you'll see an S at the end. That's for that sort of seconds. But it's still like how much total that you're making. KVP is the quality, like what the peak is, and sort of more of the shape, what's going on there, and think about that more as the quality. So there's some relationships that are testable. If you double the MA, you will double the energy spectrum. If you increase by 15% the KVP, that will also double the energy, or double the intensity of the energy spectrum. So for regular diagnostic imaging, because your exposure times are so short, you can have a really high MA like 1,000. The limits of MA and KVP are based on the tube heating and cooling. which is now automatically controlled. But back in the Stone Ages, X-ray techs had to actually manually pick the MA and the kVp and the time by guessing how fat somebody was, sort of like one of those booths at the circus where they guess your weight. And they had charts on their wall that showed maximum settings, and otherwise they would melt the tube. So let's look at some ways that this can be diagrammed. So I've got 4 different spectrums here, and the 2 on the left, or the radiologist right, are the, notice that they have the same kVp. In other words, we are going to stop here, and here is going to be the same thing because that's the max. But the spectrum is going to be, this should be double that. Why is it double? Because I doubled the MA. And notice the average energy stays the same because that's based off of the kVp. In a standard tungsten target X-ray tube with normal filtration, the average energy is going to be between 1/3 and 1/2 of the maximum energy. So if your kVp is 70, your average is going to be around 25. Now, I should point out also, in these diagrams that I've got here, we're ignoring characteristic X-ray. They're all tungsten, so they're all the same target, so it would all be the same. The point is just to show you the difference between MA and kVp. Now let's look at the yellow and the blue one here. We've increased the kVp, so now we're further out relative to this one. Further out here, it's the same here, and we also see, look, the difference here and here. Okay, so we've increased the MA and the kVp, and we've increased the kVp and the MA, and like a way this could be asked would be show these graphs, label the average energies, and then give 4 choices, A, B, C, and D, and then have you match them. You should be able to figure that out, knowing that this is going to be shorter than that, so we would pick the 2 short ones for those 2, and then we were deciding between these 2. The bigger hump would be this one, and the smaller hump would be that one, and then we could look over here and say, okay, these were the longer ones, so we knew it was the 105s, and this has more MA, so that would be the big hump, and that would be the small hump. So that would be one way this could be asked. Another way something could be asked about this would be just having you distinguish between this one versus that one, knowing that the maximum energy is going to stop right here, maximum energy is going to stop right here. And then another way would be to ask you what the average energy would be. Remember, that's going to be between 1/2 and 1/3. It's about 1/3 right here, and right here, to make you be able to guess that. That's probably about it. Now, this is another just diagram to point out the fact that that maximum energy changes with the kVp. So it's just highly testable. All right, now what changes between orange and red? So let's look at what is the same and what's different. So notice that the maximum energies are the same right here, but what's different is this and this. So this is something that I omitted from the last one. These are those characteristic peaks. Notice they're different. So different characteristic peaks mean different material. Remember that is characteristic. I'm making quotation marks in the air. This characteristic is for that characteristic material. So different material, different characteristics. All right, now let's look at this one here. What changed between yellow and orange? Again, characteristic peaks here and not seeing them here. So that's strange. How about if I told you this was actually the same source material? How about that? Now we'll notice that another thing that's changed is that the kVp's changed, right? So here's 70, sort of like right in the middle, and then out here we aren't even seeing that. So the KVP was changed, and it was lower to the point that it didn't meet the threshold that it needed to get those characteristic peaks. Remember, that was around 69.5 for tungsten to be able to generate that characteristic X-ray from the K-shell. You had your K-shell threshold. Well, we're below the K-shell threshold, and we could never have more energy coming out than went in, so we didn't put enough in. This guy put enough in. So that's what it looks like when you had sort of insufficient KVP to generate an X-ray. Boom. Okay, so if you want to double the X-ray exposure, you can either double the MAS or increase the KVP. I mentioned that before. What if you want to lower the dose but maintain a constant exposure? So you can increase the KVP by 15% and decrease the MAS by half. Now, why would you do something like that, or how does that decrease the dose? The stronger electrons, the faster ones, remember you've changed the quality now, and you've decreased the quantity, that they're actually going to fire through faster. By doing this, we kept it the same, right? So if you look at that, this kept everything the same, but what we did was we changed the quality, and that so now we've got stronger X-rays that are coming out, and they're going to penetrate all the way through, and you're actually going to get less dose because of that. They'll just shoot right through. So what if we were going to go up to the NICU and do some X-rays on babies? And you've been demoted to tech, you've been unable to pass the board exam enough times that you've just given up, and now you're a tech. And you've been sent up there, and you've got to pick the settings. What are you going to do different? Are you going to just do the same thing you would for an adult? Of course not. So we're going to do something a little bit different. We're going to, in this case, lower the KVP and keep the MAS around the same, or you could decrease it also. And the reason that you do that is babies are little and they require less KVP for penetration. Remember, you get more bang for your buck as far as decreasing overall the overall quality here, because 15% here equals 50% there. So good technique for a baby X-ray is around 65 kVp. They're small, they don't require as much juice to penetrate. And just to put things in perspective here, most adult chest X-rays are around 120 to 140 kVp. So you've really cut the dose and more than half, because you're going by 15%. And then you can use around the same MAS or lower. Good technique is between 2 and 4. Adults are typically around 4. Portables are actually closer to 2.5. So if forced to choose, I would lower them both. If that wasn't an option, I would lower the KVP first. Oh, and don't ever use a grid on a kid. I will talk about grids a little bit later, but that's something that always comes up. Never use a grid on a kid. Okay, so let's do some more vocabulary here. One of the things that we're going to talk about is this idea of the focal spot. So that's the focal spot is the part of the target where the electron bombardment takes place, and therefore X-ray production takes place. Generally speaking, a smaller anode has better spatial resolution, so why not make it as small as possible? The trade-off is heat production, so the smaller it is, it can't dissipate heat as well, so it will end up melting it eventually. So that's the limitation that you're dealing with. And you can do different things like angling the anode, which gives it a slightly larger surface area, or some devices will rotate the anode. So that's the focal spot there. And then there's another focal spot here where it lands on the patient. So the one on the target is referred to as the actual focal spot, and then the one on the patient is referred to as the apparent focal spot. The apparent focal spot is the one that defines the amount of blur, not the actual focal spot. So that's the testable point here. This is going to define your blur. Okay, blur Remember that I'm writing this. Blur. Okay. So the goal is to make the smallest focal spot as possible because that gives you your best resolution. Remember, the trade-off I mentioned is heat. So that would be one focal spot there with a larger angle, larger surface area, and a bigger apparent focal spot. So more blur. And then this would be a smaller one here, smaller angle, smaller surface area, less heat tolerance, and a smaller apparent focal spot. So less blur, better picture. The problem is, of course, that heat intolerance. So what are some other factors we can use to monkey with the focal spot? One of them is by cranking up the MA. So there's this phenomenon called blooming, where you can imagine that if you've got a whole bunch of different electrons, sort of one here and one here and one here, they repelling each other, right? Because they're all negatively charged. They don't want to be next to each other, so they're like elbowing each other out of the way. And as they move along, that actually causes the beam to widen or bloom. This is actually, the opposite is true with a higher KVP. So this is seen more with low KV. And so you can imagine, like, if you're firing two bullets like right next to each other, that they're going to be traveling so fast with so much energy that they're not going to care that they're traveling right next to each other. Whereas if you were walking slowly elbow to elbow with somebody, that would be really annoying, right? So you probably would even slow down or speed up a little bit or bump them. So think about that. Like, walking right next to somebody the exact same speed is irritating versus like sprinting like past each other. It would be less annoying, so you would get less of that. So high MA, low KV creates this blooming phenomenon, and a high KV will actually decrease it. Sometimes it's called thinning of the focal spot. All right. Now, there's an entity, a vocabulary word called the heel effect. That's a testable thing. So basically the idea is that you've got electrons coming through, striking the anode. Let's take a zoom in look here. And as they strike, they get progressively attenuated based on how much of the thickness of the anode they have to penetrate through. So the ones that get stopped superficial, like right here, they don't get as attenuated as much as the ones that travel all the way deep into the meat of the block, like out here. So why does that matter? It creates some variation where you have some of the X-rays that are generated being less intense and some of them being more intense, and that can potentially mess with the way that the picture is exposed. So there are a couple of ways that, because technologists know this phenomenon occurs, that they are trained to take advantage of it. One of them is that they want the cathode, which is going to be the spot where you have your more energetic X-rays closer to the chest wall. Why would you do that? Well, that's the part that's thicker, right? So you need more energy there. And then towards the nipple, this is in a setting of a mammogram, of course, you would have the anode where you have your less energetic X-rays. Another way that's sometimes done is when you're looking at a chest X-ray. So they want to position the tube so that they are utilizing the stronger X-rays through the part of the body that's more dense, and the weaker X-rays through the part of the body that's less dense, like the lungs. So you'd sort of position it like this. And that way you've got the cathode side down, where you're going through organs and those kinds of things that are stronger, and you don't burn out the lungs. This would be the wrong way to do it, where you have one lung that's burned out and the other lung that's less or normally penetrated. So, in a horizontally oriented fashion would be incorrect. So that's another application of the heel effect. So some ways to manipulate this. The source to image distance, it will become worse with decreased source to image distance. So I'll illustrate that for you. So this is an exaggerated Heal effect. And if we were to image here, up here, versus down here, and I'll transfer those pictures over here for you so you can see. You see the one up top really has got a lot of variation between each one of the cuts, and as we got down lower, it's more spread out and there's less variation. So less Heal effect further down, more Heal effect closer to the source. Another way to look at it is the field size. So a larger field size is worse, so I'll prove that to you. And let's say we'll start out with a small field size here, and then we'll compare that to a big one here where we're seeing a lot of variation here versus just a little bit of variation here. Another thing that can be done is changing the angle. So a smaller angle here is going to have a worse Heal effect because it's a more abrupt change. Some people will call this a Heal cutoff. So as you get a sharp transition with a small angle and you get a more gradual transition here with a larger angle. So smaller angle, greater Heal effect, and that's called the Heal cutoff. So just to review, small angle worse, closer at a shorter distance, and more field size worse. So here's another vocabulary word that's testable, is this idea of a half value layer. So what does that mean? It's basically a measurement that's done to understand the quality of the beam. So how much material is required to attenuate the X-ray beam to half its original output? That's the half value. The higher the average energy, the more penetration it will have, and the larger the half value. So a couple of words I said that I want to emphasize here. One was quality of the beam. So that's making you think like maximum energy, right? And the other one is, I said that the higher the average photon energy, the more penetrating it will be. So that's really important. So a higher average is going to go penetrate further. So with each half value layer, the average of the photon goes up. Well, how can it go up? It goes up because the wimpy lower energy photons are removed first, leaving only the higher ones. And if you average the higher ones together and you remove the lower ones from the math equation, your average is going to go up. So a third half value layer will be more penetrating than a second half value layer, which will be more penetrating than a first half value layer. Even though you've removed some of the total amount of X-rays, the average has gone up, and the average is what determines penetration capacity. That's a little bit hard to understand. You'd think, well, more would go through more. But in this case, actually less go through more if their average is higher. So that's the key. So let's compare these orange, red, and yellow ones. So here's the average with no filtration at all, right where the white line is there. And then as we add filtration, so that the orange one is where it was previously, the whole spectrum is sort of shifted forward, and there is the average energy now. I will point out to you that this never changes, right? Because that's set by the maximum energy, so that's staying the same the whole time. But sort of the back end is getting chopped off. These wimpy X-rays from here, they're hitting the road. So with a 1.5 millimeters of aluminum, we're shifting the average energy, and so the red would be more penetrating than the orange, and then the yellow would be more penetrating than the red. So it's sort of continuing to shift. So this is more of a theoretical idea here. Is the monoenergetic beam is sort of the ideal beam. It doesn't really happen in real life. The real ones are polyenergetic for all the different reasons that I sort of mentioned before. But if you were going to compare the average energies to a energetic beam and a mono energetic beam, assuming that they have the same KVP. So we'll assume that this line here is the same as this line here, that the mono energetic beam has a higher average and therefore a higher half value layer, because it doesn't have all those worthless wimpy ones at the bottom, right? So there's that. So that concludes this lecture. The next one is going to be a lecture on X-ray interaction with matter.